All right, 3.4, second derivative tells us the concavity of f in the same way that the first derivative tells us the slope of f, meaning it has to do with the plus and minus stuff. If it's positive, if first derivative is positive, f is increasing. If second derivative is positive, we're concave up as opposed to concave down. So now a little bit of detail put on that. If f is differentiable on AB, then the graph of f is concave up. Concave up on that interval, AB, if f prime is increasing. F prime is increasing. Now remember, f prime is the slope of f. So if the slope is increasing, then it's concave up. So let's try to draw a picture of something whose slope is increasing. Maybe it starts at 0, and then the next little piece over is sloped up a little bit, and the next piece is sloped up a little bit more, and a little bit more, and a little bit more. That's what concave up looks like. Now it can also extend to the other side. This one's a little bit harder to see maybe. So those little slope pieces are increasing because they go from like -8 to -6 to -1 to -1/2. And so think about a number line. They're negative, but they're increasing. So if the slopes are increasing, then you end up with concave up. So if f prime is increasing, that's the picture for concave up. You can guess the next line. F prime is concave down. On A to B if f prime is decreasing. So if the slope is decreasing. So we'll start with a really steep slope. And then the next piece over is not as steep. Not as steep. It was. So those slopes are decreasing. It used to be really steep, and then less steep, and then less steep, and then 0 steep, and then maybe it goes negative. So that's concave down. Let's put them together like on just one picture here and see if we can make a whole bunch of statements about one picture. So kind of an x-cubed looking graph. Somewhere in there, the concavity changes from being down to being up. For whatever reason, a lot of times we mark that point with like a little X. It's got a name. We'll talk about its name in a minute. So let's see. This part on the left, up until that star, so that part of the graph, is that concave up or concave down? Concave down. The slopes are decreasing. They start out really positive, they get less and less and less. Eventually the slope goes negative. So that's concave down. In fact, we could say all of those things. F prime is decreasing. Right, the slopes are getting less, which means it's concave down. Some people would say it's bowled down. Like concavity is like, how is it bowled? It makes a bowl. But is the bowl pointing down or is the bowl pointing up? Some people say, does it hold water? Does it not hold water? Just different ways to think about concavity. And if f prime is decreasing, Here's the sort of connection for the second derivative. That means the second derivative is negative. Kind of in the same way where if f is decreasing, then f prime is negative. If f prime is decreasing, then f double prime is negative. And you could keep going with that. If f double prime is decreasing, then f triple prime would be negative. And if f triple prime was decreasing, then f quadruple prime would be negative. And on and on and on. Usually we stop at 2 because the second derivative has meaning for the graph. It's concavity. The third derivative, I'm sure it's got some sort of meaning, but it doesn't show up on the picture, a third derivative. So usually we stop at the second derivative. All right, on the other side of the little x, let's see, the slopes are negative, but they're getting less negative, and eventually they go positive and get more and more positive. So that means f prime is increasing. It's concave up. It's bowled up or bowl up. It holds water. And the second derivative is positive. So like that's the lesson for today in one picture and 8 phrases, I guess. Now, there's a lot more coming, but it all comes from this idea. If the second derivative is negative, then we're concave down. If the second derivative is positive, then we're concave up. So let's find the concavity intervals of f of x equals negative x cubed plus 3x squared minus 2. Concavity intervals. So we've done intervals already. We've done increasing and decreasing intervals. And which derivative tells us increasing or decreasing? First derivative tells us that. Well, now we want concavity intervals. That's a second derivative interval. So the process is the same as the first derivative intervals with a different conclusion. So we need a second derivative. We'll set up the number line, do the whole interval test thing, but it will tell us not increasing, decreasing, but whether we're concave up or concave down. So, first derivative, and since it's just a polynomial, I don't feel bad at all about picking on people. So, Izzy, what's the derivative, what's the first derivative of our function here? Keep going, yeah, sorry. Plus 6x. Good. And so let's pause here for a minute. First derivative tells us increasing, decreasing, which can lead to maxes and mins. We can do increasing and decreasing intervals off of that. So there's a lot of stuff we can do with that. But whenever we see concavity, our brain should go to second derivative. So we need a second derivative if we want to answer the concavity question. So, Lauren, what's the second derivative then? Good. All right. Do you remember what we did on the increasing and decreasing intervals? Like, how did we know where the boundaries were? Critical number. Okay. And what was the critical number? Or how did we find a critical number? Good. F prime equals 0 or f prime is undefined. Set up our sort of boundaries for our intervals. Same thing here. It doesn't have It doesn't have a fancy name like critical number. So it doesn't, like I say, I'm going to call it something, but it's not its official name. So important numbers or boundary markers or I guess interval boundaries maybe is the. So it's like critical numbers. It's like the critical number for the second derivative, but no one has given a name to that, which is unfortunate because every calculus teacher teaches this lesson and it has this perfect parallel with the first derivative lesson, except that there's not a name for second derivative critical points. If you called it that, I would know what you meant, and any grader would know what you meant, but they don't have a name. But you don't have to call it anything. Set the second derivative equal to 0. That'll let us know where our boundary markers are. So 6x equals 6, x equals 1. Here, this interval test is nearly identical to the first derivative interval test. I mean, a key difference being that we're not going to plug it into the first derivative, we're going to plug it into the second derivative, and our conclusion isn't going to be increasing or decreasing, our conclusion is going to be concave up or concave down. But this part of the process is the same. So I need a volunteer from the left of 1. That's a good choice over there. 0 would be a great pick. And to the right of 1, pick 2. And now we have to be extra careful because when I ask where do you want to plug that in, there's 3 options. We got an F, we have an F prime, and an F double prime. Which one do we want to plug it in? Double prime, because double prime tells us concavity, and that's what we're looking for. So F double prime. So -6 times 0 plus 6. And like last time, I only really care if it's positive or negative. So sometimes if you get something weird, it doesn't matter as long as you can figure out if it's positive or negative. So F double prime is positive. What does that mean for F? Not if F prime, if the first derivative was positive, then F would be increasing. If the second derivative is positive, what does that tell me about that? Concave up. So first derivative tells me slope, which leads to increasing, decreasing stuff. Second derivative tells me whether we're concave up or concave down. And if we plug in 2, -6 times 2 plus 6. So -12 plus 6 is negative. So F is concave down. You can do the picture like we did with first derivative, but pictures are a little less meaningful for concave up because concave up, it could look like that. That's concave up. So it doesn't have to be the full bowl. That's still concave up. That's concave up. That's concave up. So I'm more hesitant to draw pictures for concavity because concave up can still look quite different. Same thing with concave down. It could be just that piece. It could be like that. It could be sort of the whole bowl looking thing. So I'm less likely to draw pictures for concavity because it's more misleading than it is helpful. Increasing and decreasing is fair to draw a picture. You can draw a picture for concavity if you want. It's just there's several different ways that something can be concave up or concave down that drawing a picture might kind of lead you astray. Let me answer the question here. Concavity intervals. Well, I've got the picture, but I haven't really said it explicitly yet. It's concave up from -infinity to 1, and concave down from 1 to infinity. So the hope is you see the parallel with what we did with the first derivative stuff. Right? Take a derivative, set it equal to 0, set up the number line, test the intervals, make the conclusion. Like that's the same process for first derivative and second derivative. It's just the conclusion is different. Second derivative tells us concavity, first derivative tells us increasing, decreasing. Questions, comments, concerns so far? So far so good then. Point of inflection. This is another thing that has sort of a first derivative parallel. Point of inflection is a second derivative thing, but when we talk about it, it kind of has a parallel in the first derivative world. You can always abbreviate it POI, including on the AP test. You can even pronounce it POI if you want. Calculus people will know what you're talking about. You know, calculus math people are always looking for abbreviations and way to do things more efficiently, so POI it is. The point C comma f of c, so that's just like an x comma y, the point, although it's kind of a side note, when it asks for a point, you got to give the x and the y. So you'll find the x, but then you'll plug it back in to find the y. So make sure you're careful of what's being asked. Point of inflection, C comma f of c. Excuse me, the point is a point of inflection. Of f if two things, f double prime equals 0, or f double prime, I should say of c, f double prime of c, f double prime of c is 0, or f double prime is, what do you think? Thinking about the parallel with first derivative, undefined. So that's sort of the critical point parallel for point of inflection, although we don't call it a critical point because that's a first derivative thing. And if f double prime changes signs. If f double prime changes signs, that's a change of concavity. So this is sort of like a max and min in the first derivative world, right? You get a critical point by finding where it's 0 or undefined, and then if it changes one way or the other, you've got a max or a min. It's kind of the same thing here, but in second derivative world, it's a point of inflection as opposed to max or min. So that point A is kind of like a critical point, and you put them together, and it's kind of like max and min. It's that same thought process of finding the critical numbers and then checking to see where they change signs. But in first derivative world, those are maxes or mins. In second derivative world, they're called points of inflection, where something changes concavity. Back up to this picture that we did earlier. So that little x right there, f double prime changed from one way to the other. So that little thing is called a point of inflection. That's a POI, point of inflection. Guess where it's not like the max and the min is that max and min are specific to which way it changes, right? If f prime changes negative to positive, that's a min. If f prime changes positive to negative, that's a max. Second derivative, it doesn't matter which way it changes. If it changes, it's a point of inflection. There's not a special name for changes, concave down to concave up, or concave up to concave down. There's not a difference between those. It's still just a point of inflection. Second derivative test. Let's draw the little roadmap again, because the second derivative test is another path we could take on this little decision flowchart roadmap thing that we've drawn a bunch of times already. Let's just start from the beginning here. So we get critical points. That's where f prime equals 0, where f prime is undefined. That tells us what the possible extrema are. And then now we're going to have three paths to take. So the first path we learned led to absolute max and min. So that was number 1 on the quiz yesterday. Yeah, that was number 1 on the quiz. So what was the name of this route that you took to land at absolute min and max? Or what did you do? Table of values. And when you use the table of values, did you plug it into f prime, or f double prime? F. You had your table was x and f of x, or x and y. And then you just grab the tallest y and the shortest y for your max and for your min. That's one route to take that takes you to the absolute max and min. Second thing we've already done is a relative max and min. And what was that route called? The first derivative test. That was not on the quiz. That's where you do the intervals of f prime. And you've got increasing, decreasing, increasing, that sort of stuff. And that tells you where you've got a relative max and a relative min. Well, today, third option is the second derivative test. And by the way, this is the last option. We're going to stop adding on to this roadmap here. But there's 3 different ways to arrive at max and mins, and it kind of depends on what kind of max and min you want. Second derivative test leads us to a relative max or min. And so now we need to talk about what the second derivative test is. So this is sort of how it fits into the big picture of finding a max or a min, but now we need to figure out how to use it. And I think the confusing part for students is we usually think of first derivative telling us stuff about maximum and minimum, second derivative telling us about concavity, and second derivative does tell us about concavity. But even just drawing the picture, you can see if something's concave up, it's probably got is that a max or a min? That's a min. If something's concave down, it's got a max. So that's sort of what's going on with the second derivative test. So that's the big picture view of where we've been, and what we're doing today is the second derivative test. Alright, so let's talk about the second derivative test. Let f be a function such that f prime of c equals 0. What does f prime of c, f prime equals 0? Give me some other words that means, or pictures with your hands. If f prime is 0, what does that mean? Yeah, a lot of this. So a horizontal tangent line, it's flat there. It might be a max or a min. So all of those things should be running through our brain when we see f prime equals 0. So if f prime equals 0, and f double prime exist, yeah, we can just pause there. If f double prime exists, then here's our conclusion. Here's two different things that could happen. So this is 1 or 2. It's not both, it's one or the other. If the second derivative is greater than 0, second derivative is greater than 0. What does that mean about concavity? Concave up. Then f of c is a... Alright, well, let's draw a picture of something that is concave up but we also want the spot where the derivative is 0, so where there's a horizontal tangent line. And that would be right there. So if we have both a horizontal tangent line and it's concave up there, then what kind of point is that? A minimum. Let's put relative on there because we don't know what else is going on. There could be lots of minimums, and it might not be the lowest minimum. Or if f double prime of c is less than 0, then f of c is a, well, you can figure out what's there just because, you know, we switched some things around, but let's draw the picture again. We want the second derivative to be negative. That means concave down. So there's concave down. But we also said, part of the initial part of this statement was f prime is 0, so that's a horizontal tangent line. So that spot is a relative max. So the second derivative test is if f prime is 0, which we've already covered kind of from the critical point, then you check the second derivative, and if it's concave up, you've got a min. If it's concave down, you've got a max. This is another one where you should not memorize this thing. You should think about this when it comes up. If it's a horizontal tangent line, but it's also concave up, then that's a minimum. So don't memorize all the combinations. Think about them, and you can reason through what's going on.
So if we can find relative max and relative minimum with the first derivative test, why do we do the second derivative?
Okay, great question. Question was if we can use the first derivative test to find a relative max and min, why do we even need the second derivative test? It's a good question, and you're right, but that's a big if. If we can do this, then we don't need this. You are right. The AP test less so me, but I'm learning as I take more AP tests. They're good at figuring out how to write questions that force you into the second derivative test. So it's a good question and a valid concern, like, well, if I can get there this way, it's like a second route to the same, if I know how to get home from the school, why do I need to go a different route? Like, I know how to get there. Well, sometimes AP will block this route. Sometimes I will block that route based on what I give you in the problem, and it will force you into this route. So it's a good question, but we know how to put the blockade up in the fire drill to make you take the alternate route. All right, let's do an example. Let's find the relative extrema of f of x equals 2x cubed minus 3x squared minus 12x plus 8. And then to get around Connor's valid concern, we'll say using the second derivative test. So that's one way to force you into it. I'll just tell you to use it. But there are other ways. We can set up the problems in tricky ways that force you into the second derivative test. Okay, using the second derivative test. So I'm thinking about the roadmap. I still need critical points, so I know what to test. And then I need a second derivative to test them into. So first derivative would be 6x squared minus 6x minus 12. It is nice when they sort of rig these things to work out for you, because I'm going to want a second derivative, but I also want to know where this is equal to 0, because I'll need those critical points. So factor out a 6. So my critical points then are x equals 2 and x equals negative 1. Had a couple people on the quiz yesterday tell me on this type problem that x is equal to 6 or that x is equal to 0. No, right? There's no x out there, so that 6 doesn't really add any answers for me. So those are my critical points, but since we're using the second derivative test, I need to find the second derivative to plug those in. So another way to say this is, these are places where the first derivative is 0, so those places have a horizontal tangent line. What I don't know yet is, are they bowled up or bowled down? So I don't know yet if they're maxes or mins. So a second derivative then would be 12x minus 6. So let's check our 2 points. At x equals 2, f double prime of 2 equals positive, right? 24 minus 6 is positive. So at x equals 2, if the second derivative is positive, that means we know there's a horizontal tangent line. That's from first derivative equals 0. Second derivative is positive, tells us what about concavity? Concave up. So again, I don't have this combination memorized. I think about it every time. If we're concave up and there's a horizontal tangent line, like what's going on at x equals 2? That's a relative min. At x equals 2. Again, I don't memorize that combination of stuff, I think about it. First derivative 0 means I've got a possible max or min. It's concave up versus concave down. At x equals -1, 12 times -1 minus 6 is negative. So that means we are concave down. And we already established that we had a horizontal tangent line. So if we're concave down and we have a horizontal tangent line, then we've found a relative max. We should be careful here. That's at x equals -1 as opposed to x equals 2. So advantages, disadvantages of the second derivative test. Advantage is you plug in the exact number into the second derivative. You don't have to set up a number line. You don't have to look for intervals and you plugging a bunch of numbers in and looking for where things changed. So in some ways it's a little bit more direct because you're just plugging into the second derivative. The challenge would be it's not always easy to find a second derivative, right? Sometimes the second derivative is then, you got chain rule and quotient rule and it's a mess. So it kind of depends on the problem as to which one is better or necessary. Let's do one more. We'll do this one quick. You thought we were done. Find the relative extrema of f of x equals -3x to the 5th plus 5x cubed. Again, we're going to go a little faster on this one. So f prime of x is -15x to the 4th plus 15x squared. I do need a second derivative, but first I'm going to factor out a -15x squared. That leaves x squared minus 1. Set that equal to 0 to give me my critical points. And since it's equal to 0, I'm also finding my horizontal tangent lines. These are the possible extrema. So x equals 0. Right there. What else might x be? Plus or minus 1. You can write them separately, or you can just write plus or minus 1. Second derivative. So that would be -60x cubed plus 30x. Which feels like we're getting a little bit ridiculous here, but we're only going to be plugging in zeros and ones, so it's not that big a deal. I'm just trying to organize my thoughts here. So at those three spots, the first derivative is 0, so those are potential maxes and mins. Now let's find their second derivative, because that'll tell us whether we are at the bottom of the valley, the top of the hill. So f double prime of -1, goodness, that's going to be 60 minus 30, right? Because -1 cubed is negative, times -60 is 60, minus 30 is positive. So what's going on at -1? If the second derivative is positive and the first derivative is 0, it's concave up. And again, there's nothing wrong with doing a little picture every time. Concave up, first derivative 0, so that's a relative min. And as especially after yesterday's quiz. You guys, you have to show your work on this stuff. This is how you justify your answer. You can't just say, oh, it's a relative min. Like, how did you know that? Tell me, explain to me, show me. How about f double prime of 0? What's that equal to? 0. So, no conclusion. It's not a max or a min. There's nothing, it can't really say anything more than that. So it might be a point of inflection if it changes concavity there. But all I know right now is it's not a max or a min because it doesn't have concavity. F double prime of 1 would be negative 60. So that's concave down. We already said it was a horizontal tangent line. So that's a relative max. Roughly what this graph looks like. Is something like that. So there's our min, there's our max. There's a flat spot, but it's not a max or a min. All right, we went the whole time today, but no new notes tomorrow. So we'll work some of these problems together. I have one. I hesitate to call it a worksheet. It's a worksheet. It has one problem on it with like 10 questions. So tomorrow is not a whole lot of new information. Actually, it's no new information. It's just we'll work some of these together. We'll work through the worksheet together, and you won't have any new homework assignment tomorrow. So yes, today was long, but catch up tomorrow basically.